Okay, let's do some examples of continuous function problems. Okay, so let's first start with this one. At what points is the function, say f of x equals the square root of x plus 1 minus 1 over, say, x plus 2 plus the sine of x continuous. Okay, so this is a root function, so it's going to be continuous on its domain. This is a rational function, so it's going to be continuous on its domain. X is continuous, 2 is continuous, the sum is continuous. The quotient is continuous as long as the denominator isn't 0. Those were some of our rules from that function arithmetic stuff. And the sine, we don't have any rules that tell us that the sine is continuous, but the sine's continuous, the cosine's continuous, the tangent is continuous everywhere that the denominator of sine divided by cosine was not 0, so it's continuous everywhere where the cosine wasn't 0. But we can kind of base our determination of where this is continuous on what the domains of these functions are. So the domain of this first part is we want x plus 1 to be bigger than or equal to 0, right? So the domain of that is x is bigger than or equal to 0. And we know that f will be continuous on all of that stuff because it's continuous here. It's also continuous on all of this stuff for r. And then it's going to be continuous as long as x is not equal to 2. This is the domain here is x plus 2 is not equal to 0. So this is x does not equal negative 2. Right? So as long as we're in both of these things, I'm continuous here and I'm continuous here. So I want to be in both of these things. I need the intersection of them. The x values where f is continuous is, and this is all of r, it's continuous here for all of r, so it's going to be x is bigger than or equal to 0 intersected with x is not equal to negative 2 intersected with all of r. Okay, so what does that mean? The intersection's where all three of these things happen at the same time. Intersecting with r doesn't really do anything because there's no restrictions there. Here I need to be bigger than or equal to 0, and here I just can't be equal to negative 2. So this says make sure that you're bigger than or equal to 0 and then take away this negative 1. I don't really have to actually take it away because I've already taken it away when I required myself to be bigger than or equal to 0. So the intersection there is x is bigger than or equal to 0. This will be all of the points where that is continuous. Okay, so finding where a function is continuous, we can kind of break it down into pieces and take their intersections to see where we have continuity. Let's do another type of problem. Let's say what value of k makes f of x, this is going to be a piecewise function, f of x is, let's say, kx plus 1 if x is, let's say, bigger than 2, and it's going to be for minus x squared if x is less than or equal to 2. What value of k makes this function continuous? Okay. Well, what do we want to be continuous? It's a line here. Any k value works for this bit. This is a parabola, so any k value works for that bit. So if I was to draw this piecewise function, I'd draw a line on the right-hand side, I'd draw a parabola on the left-hand side, and those two parts would be continuous for sure, right? I say on the right-hand side, I'd have this line of slope k. So at 2, I have a line over here, and it's got a hole on the end of it. And then over here on the right-hand side, I have this parabola bit. It's got a solid dot on it, right? And the k value, I can adjust the k value to move this line, right? The line would always have an intercept here if I would continue dot with dots to the left here. So what I want is I want to fill in this hole with the line so it looks like this. The hole is right where the end point of the parabola takes off and comes this way. So I want these two things to match up so that I could draw this without lifting my pencil. Okay, so what I really want to do is I want to take the limit from the right of this, and I want to set it equal to the limit from the left of this. Okay, so we want the limit as x goes to 2 from the right of kx plus 1 equal to the limit as x goes to 2 from the left of 4 minus x squared. We want those two things to be equal. Okay, this is continuous, this is continuous, so the limit from the right would just be evaluation there, the limit from the left would just be evaluation there. So we want kx plus 1 when x is equal to 2. So I'm going to not put an x there, I'm going to put a 2 there. Equal to, it's a 1, equal to 4 minus 2 squared. Because I'm evaluating this guy at 2. So I want k times 2 plus 1 equal to 4 minus 4, which is equal to 0. So I want k equal to minus 1/2. Which, well, that's good because that looks like a slope of minus 1/2, so our picture is going to kind of work out right. Even though, well, this parabola would be up here and so on, but I still want this hole to fill in there, and to do that, I'm going to set k equal to 1/2. K equal to 1/2 makes the two endpoints at 2 match up. Okay, another type of problem that we have for continuity type stuff is, well, let's draw a picture and I'll kind of explain this first. Right, maybe I have a function that has a hole in it here, and maybe the function value is up there, but I could change that value to fill in the hole. If the limit from the left and the limit from the right are both equal, I could sort of fix this hole and make it continuous. So one short example of this is, say, x squared minus 1 over x minus 1. Well, I can't actually plug in 1 here because then I get 0 over 0, but I can fix the hole by dividing things off. This is x plus 1, right? So I could fix that hole at 1 by just thinking of it as x plus 1 without a hole in it, right? The graph of this would look like x plus 1, but it would have a hole in it there. We're going to fix that hole by plugging in the hole and setting the whole function to be x plus 1 because the algebra worked out. Okay, so let's do a problem like that. It's a can we fix this problem. So can f of x equal to, let's go with 1 minus cosine of x over x squared be made continuous at x equals 0. Okay, right now it's discontinuous at x equals 0, right? I've got this cosine function. Cosine's everywhere continuous. 1 is everywhere continuous, so the numerator is everywhere continuous, and the denominator is everywhere continuous. But when you take that quotient, it's not going to be continuous at 0 anymore because I can't divide by 0. So this is discontinuous at 0, but can we fill in a hole there? Does it have a hole there? Does it have an asymptote there? What kind of discontinuity does it have? Well, we want to see if that limit as we get close to 0 exists. So can it be made continuous is the same question as, does the limit as x goes to 0 of f of x exist? If it exists, we can fix that hole at 0 by just setting f of 0 to be equal to that limit, and that just fills in the hole. Okay, so we're going to take this limit as x goes to 0, 1 minus cosine of x over x squared. We're going to see if we can do this. Well, this will be, we're going to use our trig difference of squares idea. So I've got this limit, x goes to 0, 1 plus the cosine of x, and 1 plus the cosine of x. That's where we're going to multiply the top and bottom by that, and I have 1 minus the cosine of x over x squared is the original stuff. So we're going to multiply top and bottom like this, and I'm going to end up with the limit as x goes to 0 of 1 minus cosine squared of x divided by 1 plus cosine of x times x squared, which is equal to the limit as x goes to 0 of, I'm going to rewrite this as 1 over 1 plus the cosine of x times 1 minus cosine squared is sine squared, so this is going to be sine of x over x, and I'm going to square that. I'm going to write it like that because we know what sine of x over x does. It goes to 1, right? So this goes to 1. This, as I get close to 0, goes to 2, or to 1/2, right? The denominator goes to 2. So this is equal to 1/2, and so that limit does exist. So we could fix this discontinuity at 0. We would set f of 0 equal to 1/2. And then the function value is equal to the limit, which is the definition of continuity. Okay, if you want, you can go to Desmos and you can graph this function here, and you'll see at 0, it's going to approach 1/2 from both the left and the right. I don't know if Desmos will give you a hole in the graph or not, but we could fix it if it did. If it doesn't, Desmos already knows that we can fix it. So you can graph that and see kind of how that hole gets fixed. Okay, that's it for 2.5. I hope you guys have a good Labor Day weekend.